What do a stock portfolio, a rainy weather forecast, and an electron spin have in common? They're all uncertain, and they're all described by the exact same piece of math. By the end of this video, you'll be able to calculate the average, the risk, and even the shape of any random outcome, whether it's your investment returns or the spin of a single electron. Let's get into it. Let's start with the core idea. Expectation is just a probability-weighted average. Not a simple average, a weighted one, where more likely outcomes count for more. Let's start with the core idea. Expectation is just a probability-weighted average. Not a simple average, a weighted one, where more likely outcomes count for more. Here's the twist that trips people up. You will never actually win 5.80 in a single play. Nobody hands you 80 pences of a pound coin. And this idea shows up everywhere, not just gambling or finance.
3 outcomes, each with a probability. Multiply, add, 2.5 rainy days. Not what will happen, what to expect. When a drug trial says this medication will reduce your pain, what exactly does that mean? Not a promise, not even a prediction. It's an expectation, a probability-weighted average. Maybe half of patients feel nothing. Some feel modest relief. A few feel dramatic improvement. You take each outcome, multiply it by how likely it is, and add everything up. That sum, that single number, is the expected value, not the most likely outcome, the balancing point. Each item can have 0 defects, 1 defect, or 3 defects. Expected value weights each outcome by how likely it is. So common outcomes count more, and rare outcomes count less. Multiply each defect count by its probability, then add them together. That gives 0.35 defects per item, about 1 defect for every 3 items.
Same formula, completely different worlds. That's the power of expectation. It's a universal language for describing uncertainty. Now here's where it gets genuinely strange. In quantum mechanics, this exact same math describes something much deeper than a game of chance. We find the average spin because one measurement is random, but many measurements reveal a pattern. There are 2 possible results, plus h over 2 and minus h over 2. Spin up happens with probability 0.7. Spin down happens with probability 0.3. Because spin up is more likely, the results do not balance to 0. So we use expected value. Multiply each spin value by its probability, then add them together. The positive side contributes 0.7 times h over 2. The negative side contributes 0.3 times minus h over 2. Together, that leaves 0.4 times h over 2. So the expected spin is 0.2h. That means the long-run average is slightly positive. And just like the casino game, no single measurement will ever give you 0.2 h-bar. Every individual measurement gives either plus h-bar over 2 or minus h-bar over 2. The 0.2 h-bar is the average over many identically prepared electrons. Knowing the average isn't enough. Two situations can have the same expectation but wildly different risk. That's what variance measures, how far outcomes typically stray from the mean. Think of a coin. If heads equals 1 and tails equals 0, then a fair coin has an average of 0.5. But when you flip the coin, you never actually get 0.5. You only get 1 or 0. So 0.5 is the long-run average, not a single outcome. Same idea here. For electron spin, one measurement can only give plus 1/2 h-bar or minus 1/2 h-bar. But because one result is more likely than the other, the average over many measurements comes out to 0.2 h-bar. That average tells us the balancing point. Variance asks the next question. How spread out are the real measurements around that average? The shortcut is expected SZ squared minus the mean squared. SZ squared is always h-bar squared over 4, because squaring removes the sign. So expected SZ squared is 0.25 h-bar squared. Then subtract the squared mean, 0.2 h-bar squared, which is 0.04 h-bar squared. 0.25 minus 0.04 gives 0.21 h-bar squared. And the standard deviation is about 0.458 h-bar. That means the real measurements are typically almost half an h-bar away from the average. If the electron were guaranteed to be spin up, probability 1, the variance would be exactly 0. No spread, no uncertainty, no surprises. Variance is 0 precisely when there's nothing left to predict. So far we've used outcomes you can count, up or down, 0 or 6 or 20. But some quantities, like position, can take infinitely many values. That's where we swap sums for integrals. The particle bounces freely between the walls. Its position is a continuous random variable, uniformly spread across the whole box. That flat line is the probability density.
For a continuous position spread evenly across the box, the expected position is the center, L over 2. The standard deviation is L over square root 12. That tells us how widely the position is spread around that center.
Mean and variance describe center and spread. But two distributions can share both and still look completely different. That's where skewness and kurtosis come in. Skewness tells us whether a distribution has a longer tail on one side. A long tail means that although most outcomes are clustered together, there are a few rare outcomes that are much more extreme. If the tail stretches to the right, we call it positive skew. Most outcomes are small or ordinary, but once in a while there is a very large positive outcome. If the distribution is balanced, the skewness is 0. That means the left and right sides are mirror images, so positive and negative deviations are equally likely. If the tail stretches to the left, we call it negative skew. Most outcomes may look normal, but occasionally there is a very large negative outcome. In the stock market, skewness tells us the direction of tail risk. Positive skew means rare but very large gains. Think of a small biotech company that usually moves very little, but occasionally jumps dramatically after successful clinical trial results. Negative skew means rare but very large losses. Imagine an investment strategy that earns small profits most days, but occasionally suffers a severe market crash. So variance tells us how spread out the outcomes are. Skewness tells us which direction the extreme outcomes lie. That is why two investments can have the same average return and the same volatility, yet have very different risks, because one is exposed to rare crashes, while the other has the chance of rare windfall gains. Positive excess kurtosity means extreme events, crashes, spikes, outliers, happen more often than a normal model would predict. Kurtosis tells us how much probability sits in the extreme tails of a distribution. A distribution with high kurtosis has more rare, unusually large outcomes than a normal distribution. In markets, that means extreme gains or losses happen more often than a simple bell curve model would predict. So variance tells us ordinary spread. Kurtosis measures the risk of extreme surprises. When excess kurtosis is above zero, the tails are heavier and extreme events are more frequent. This single number is a big part of why once-in-a-century market crashes seem to happen every decade or so. So here's the through line. Master these 4 ideas, and you can quantify uncertainty in any system, from a coin flip to the strange quantum world of electrons and photons.